A tutorial on pressure and the relationship between force and area. Low pressure means that a force is spread over a large area, while high pressure means that that same force is concentrated on a small area. To illustrate that, we're going to use this rather strange example. Let's say a hat of 2 kilograms, ow, is sitting on a smiley. So 2 kilograms is 20 newtons force. But Smiley is still smiling because the pressure is not great. The force is spread over a large area of the hat. If we turn that hat upside down and that 20 newtons is concentrated on the point or tip of the hat, Smiley is not Smiley anymore because the pressure has increased. The force is concentrated on a tiny area. Same weight in both cases, but much more pressure on this side because the force is concentrated on that tiny area. There will be many advantages of increasing pressure. For example, if you wanted to scale an icy mountain, you're going to have to use ice boots. Ice boots allow the climber to scale steep ice faces as the boots dig into the ice surface. This is because the force is concentrated on the small area of the spikes, making the pressure great enough to dig into the surface. Some other examples of increasing pressure. Rugby boots. Increase pressure due to the small area of the studs. Allows the boots to dig into the ground so players don't slip. Snow chains. Increase pressure due to small area of the chains which make contact with the ground rather than the tire. Allows the wheel to dig into the snow. Here are some examples where lowering pressure is an advantage. Skis increase the contact area, so reduce the pressure. So you have the same force acting over a bigger area. With no skis, you might sink into the snow because of the higher pressure. Same force acts over a smaller area, your feet. Some other examples of lowering pressure. Well, narrow tires is actually increasing pressure. They're not suitable for off-road. The wider tires on the 4x4s reduce the pressure because the force is spread over a large area. This means you're able to drive over softer ground. Wider straps on backpacks lower the pressure on the shoulders because the force is spread over a wider area. To work out pressure, you divide the force by the area it is exerted on. So pressure is the force exerted per square meter. Or put another way, pressure is the force per unit area. Unit area stands for 1 square meter. So it's measured in newtons per meter squared or pascals, and 1 pascal is equal to 1 newton per meter squared. So the formula looks like that. P is F divided by A. Just a note on pascals. The unit for pressure comes from the name of a French scientist. 1 pascal is 1 newton per meter squared, or written 1 newton m to the minus 2. And remember, you can make a magic triangle for pressure. If you're looking for pressure, it's F over A. If you're looking for force, cover the force and you end up with PA or P times A. And if you're looking for area, cover the A and you end up with F over P, or force divided by pressure. Here's some problems. Calculate the pressure exerted by a 50 Newton force that is applied to a 2 square meter area. I'll pause for a second and you can try work that out yourself. Hopefully you paused the video. Now let's look at it. The formula, we want the P because we asked to calculate pressure, so it's F over A. Substitute the values and you get 25 newtons per meter squared, or 25 pascals. A 90 kilogram skier stands on his 4 kilogram skis, which have a total area of 0.2 square meters. Calculate the pressure exerted by the skier on the snow. So I'll pause again, see if you can calculate that. Again, hopefully you paused the video. Here we go. The force will be the weight of the skier and his skis. Now remember, to calculate weight, you just take the mass and you multiply the acceleration due to gravity. So the mass is 94, 90 plus 4. Acceleration due to gravity is 10, so 940 newtons is the force. Then we asked to calculate pressure, so again F divided by A, 940 divided by 0.2, and you end up with 4,700 Newton per meter squared, or pascals. How about a problem where you've got to do a bit of a comparison? The student of mass 40 kilograms uses the football boots. One boot without studs, that's the one on the left, has a surface area of 165 square centimeters. If you convert that to square meters, it's 0.0165, and that's the area in contact with the ground. The other boot with the 6 studs has only 6 square centimeters. And your problem is to calculate the pressure exerted by each boot. So we've got the 40 kilograms, we've got the 0.0165 square meters for the one boot, and the 0.0006 square meters for the other boot. So I'll transfer those to the next slide. And what we're going to do is work out the pressure of the first one. So it's going to be 400 divided by the area, which is that value there, 24,000 plus change. And I'm going to write pascals as the unit. And the second one is going to be the same weight divided by the new area, and we're going to get 666,000 plus change. 3 more problems. A sheet of thin ice will crack if the pressure is more than 2 kilopascals. That's 2,000 pascals. A 100 kilogram man wants to walk on the ice. What must the minimum area of his shoe be? Comment on the answer. I'll pause and see what you can make of that problem. Right, hopefully again you've paused the video. So let's have a look at this problem. We're looking for the area. So if we use our magic triangle, the formula becomes A equals F divided by P. Force divided by pressure. So the force, remember, 1,000 newtons, 100 kilograms times 10, and 2,000 kilopascals. Well, that works out to be 0.5 square meters. Now what would your comment be? I suppose your comment would be about the size of the enormous shoe, a half a square meter. However, if you look at the shoe, the snowshoe that they would use, it would be around about that area. Second last problem. The base of a water container has an area of 0.025 square meters and can withstand a pressure of 5 kilopascals. Calculate the amount of water that can be added to the container, remembering from the density of water that 1 liter is 1 kilogram. I'll pause so that you can pause the video again. Right, using the magic triangle, F is going to be PA, so pressure times area, 5 kilopascals, so 5,000 times the area, which gives you 125 newtons. Now that's the weight of the water. So to find the mass, divide by 10. So 125 divided by 10 is 12.5 kilograms. And then each kilogram is 1 liter. So the final answer is 12.5 liters. And a last problem. Why is there more pressure under a woman's stiletto high heel shoe than an elephant's foot? Well, we'll assume the elephant standing on all 4 big feet as shown in the picture, and the woman is about to take 1 step onto her stiletto heel, so all her force or weight is exerted on that small area. Well, if we had to give this as a descriptive answer, we'd say something like this. An elephant's weight is about 100 times that of a woman. but the area of one stiletto heel is more than 100 times smaller than the area of the elephant's large feet. The elephant's large weight or force is spread over a relatively large area, which means lower pressure compared with the woman's weight being concentrated on a very small area. My goodness. Let's do a calculation to check out if this is true. Having checked the stats on Google, mass of an elephant about 5 tons, so 5,000 kilograms. The area of 1 foot, about 640 square centimeters, so 4 feet would be 4 times that. And for a woman, 50 kilograms, and the area of just the one heel, 2 square centimeters. So working out the pressure, first of all, the 50,000 newtons divided by the area, and you get 190,000 plus change pascals. For the woman, you've only got 500 newtons, but it's now concentrated on that tiny area, and you get 2,500,000 pascals. So the pressure exerted by the tiny woman on a tiny area is much larger than the pressure exerted by the huge elephant on the huge area.